Well, now that we're familiar with what balanced field length is, and we're familiar with some of the nomenclature that we're using, let's talk a little bit about the accelerated climb phase. So in order to find out what the balanced field length is, or the FAR takeoff distance is, we have to be able to calculate the distance traveled in an accelerated climb. And in order to do that, we have to understand what's going on with the aircraft during this phase. So just to recap, the FAR takeoff distance, that's this SOC, is the distance required for an aircraft to accelerate to the rotation speed, rotate, and then take off and reach an obstacle clearance height. And we've talked before that the liftoff speed by FAR regulations has to be 1.1 times the stall speed, and the obstacle clearance speed has to be 20% above the stall speed, or 1.2 times the stall speed. So there's this distance SC required for the aircraft to go from liftoff to the obstacle clearance height and reach a steady climb angle. We've talked before about what the ground roll is. That's this SG, which is composed of an acceleration phase and a rotation phase. So we can calculate the ground roll, or at least approximate it. And after this video, we should be able to approximate the takeoff, this climb distance. Okay. Now this phase right here, from the point of takeoff to the obstacle clearance height, is known as transition. And the reason it's called transition is because the aircraft is transitioning from the liftoff configuration to a steady climb configuration. So we're going to be referring to this phase as the transition, or the transition distance. So this S sub C is the transition distance. Okay, so you'll notice I came equipped with some nice pre-drawn figures here, and I have another one right here, which I'm going to have to move just a little bit. Oh, here, we'll move the screen for that. Okay. So here we have this nice free body diagram. Let me label a couple things on it. Okay, so this line here, this white line, is the horizontal, and for some reason, let's move this guy up to where I want him. For some reason, he fell down a little bit. My pre-drawn figures didn't work as well as I wanted. Okay, so this white line here is the horizontal, and you'll notice this red dashed line is tracing a curve. Okay, so we are in accelerated climb, which means that we are moving from a horizontal takeoff configuration, and we're getting to a constant climb angle. So that means the climb angle is changing as we go. So we're following a curved path here. And of course, this angle here is the climb angle, gamma. But there's a radius of curvature along the arc that we're traveling. Okay, and we're going to label that capital R. Okay, so a couple things to note. Gamma is a function of time. Our velocity is a function of time. So these are things that are changing with time. And then we have forces on the aircraft. So we have our typical forces. We have thrust, which we're going to assume is aligned with the direction of flight. We have lift, drag, and weight, which are aligned. Lift is aligned perpendicular to the direction of flight, drag is aligned parallel, and weight is straight down. Okay, so I think that's all we need to label on here for now. Okay, because we're in curved flight though, there is an angular, or a centripetal acceleration that happens. We talked about this a little bit with the coordinated turn, where in a coordinated turn, the apparent force is out the bottom of the aircraft. Well, here in an accelerated climb, we have a force, a centripetal force, that is also pointing out the bottom of the aircraft. And we're going to call the centripetal acceleration A sub R. And if you'll recall from dynamics, A sub R, I'm sorry, I want to do this in a different color just for clarity's sake. Let's use green. A sub R is equal to V squared, where V is the tangential velocity, divided by the radius of curvature, capital R. Okay, so hang on to that for just a minute. Well, let's go ahead and apply Newton's second law to balance the forces here. Okay, so remember we're going to say that the mass times acceleration is the sum of the forces. So let's look at the direction of flight first. So we do have acceleration because our velocity is changing with time. So let's do mass times acceleration, where mass is the weight divided by the gravity times the acceleration, which is dv dt, and that equals the sum of the forces. So we have t minus d minus w sine of gamma. Okay, so that's the component of w here. Remember, there's two components, and this is gamma. Okay, so w sine gamma. Okay, so that's in the direction of flight. Now let's look at the direction towards the center of curvature here. So in this case, we're going to have the mass, w over g, times the acceleration. Now, the acceleration here is the centripetal acceleration, so we have v squared divided by r, and that's going to equal the lift minus weight times cosine gamma. All right, so now we have two equations. Now, let's simplify this second equation a little bit. Okay, sorry, I kind of want to keep this on here if I can. I hope I can fit everything. I'm just going to come over here to do some interesting relationships. So I'm going to put this in a box. Okay, so we're going to call the change in gamma the change in time. So remember that our climb angle is changing with time, and the change with respect to time we're going to call capital omega. Okay? All right, so let's recall from our dynamics class, which hopefully you've had. When we're talking about we can relate the radius of curvature with the arc length, which is the distance traveled along the arc here, to the rotation angle. Okay, so let's just do a little bit of geometry here. Sorry, I'm going to scroll up a hair. So we have this angle here, this gamma. But you'll notice the radius of curvature and the velocity are perpendicular to one another, which means that we can also project gamma here. So this is gamma. So gamma, in addition to being our climb angle, is also the angle of rotation. Okay, and we can relate the radius of curvature to the arc length and the angle of rotation by saying gamma equals, I'm going to call this S gamma. So the arc length here is S gamma. So that's the distance traveled from, here to here along the arc. And that divided by R. Okay, but notice we have, if we take the time derivative of this, our radius is not changing, but we have d gamma dt equals, and ds gamma dt is just the velocity. Okay, so we have velocity divided by r. And we call d gamma dt omega, so we can rearrange this equation to give us an expression for omega. So omega, which is d gamma dt, equals v over r. And if we rearrange this to solve for r, then we get r equals v divided by omega. Okay? All right, so if we plug this relationship here into this equation, then we get, I'm going to come all the way over here. So we get w over g times, and I'm going to simplify. So we have v squared divided by v over omega. So the v squared and the v cancel, and we're just left with v omega equals L minus W cos gamma. Okay, but for the purposes of what we're doing here, we're going to go ahead and rewrite gamma, or this capital omega, W over G, V, d gamma dt equals L minus W cos gamma. Actually, you know what? Now that I've done that, I'm going to change my mind. Let's just leave it as omega. Okay? And we're going to call this equation, we're going to give it a name, and that name, as always, is very imaginative, star. Okay, so that's one relationship. And we're going to, okay, so now we're going to take our drag equation, or our force balance in the direction of flight, and we're going to rearrange that as well to solve for sine gamma. And so after some algebra, what we get then is sine of gamma equals t minus d divided by w minus 1 over g dv dt. Okay, and we're going to call this guy double star. Okay, so let's think about this for a minute. We have a force balance, but what are we really looking for here? Well, the ultimate goal here is to figure out SC, or the transition distance. Okay? So I want you to keep that in mind as we go through these next steps. Okay? Because we're going to do a few somewhat tricky things. Okay? All right, so let's consider the velocity here for a minute. So our velocity has two components. There's a horizontal component and there's a vertical component. And of course, those are changing with time. Okay, but also those are related to the, to the position of the aircraft. Okay, so the change in altitude of the aircraft with respect to time would be the vertical component of the velocity, and then the change in horizontal distance with respect to time is the horizontal component of the velocity. So let's just write that, what we just said, down. Okay, so change in height with respect to time is going to be same as the climb rate. Okay, it's the vertical component of velocity, and it's just v sine gamma. Okay, and then alternatively, the change in horizontal distance s with respect to time, we're going to call v horizontal, and that's just v cosine gamma. Okay, but we have an expression for sine of gamma here in double star, so if we plug double star into here, then we can get a new expression for dh dt, where dh dt is equal to t minus d divided by w v minus v over g dv over dt. Okay? Now we have, if we use this expression here and solve it for v and plug that into here, so hold on just real quick, I'm going to rearrange this thing. So this thing implies then that v equals 1 over cos gamma ds dt. Okay, so really we're plugging that guy in for v, and then we're going to do a rearranging here. So we're going to multiply through by w and move this term to the other side. Okay, so if you'll bear with me, I'm not going to go through all the details of that, but it's fairly straightforward. Okay, so performing all those things at once, we end up with this: t minus d divided by cos gamma ds dt equals w dh dt plus w over g times v times dv dt. Okay, so this is a good news, okay? Because remember, what we're trying to find is s. We're trying to find the horizontal distance traveled, and now we have s in the equation. Of course, it's a derivative of s that we have in the equation. So what we need to do now is we need to integrate, but we can do that by separating variables. So if we multiply the dt over, and we get something, and then integrating, we get something like this. So we get t minus d divided by cos gamma ds equals the integral of w dh plus the integral of w over g times v dv. Okay, and we're going to integrate from the liftoff speed to the obstacle clearance location. Okay, so from liftoff to obstacle clearance. So in the case of velocity, it's the liftoff speed to the obstacle clearance speed. In the case of h here, it's 0 to the obstacle clearance height. In the case of s here, it's from I guess it would be sg to soc. Okay, so now we have this nice equation. We can actually integrate these terms on the right hand side really easily, and that gives us the integral from liftoff to obstacle clearance t minus d divided by cos gamma ds equals whoc, pardon the smudge, because remember that h liftoff is 0, plus, let's see what we have here. We're going to have w over 2g times VOC squared minus V liftoff squared. All right, so we have this nice equation that can be used, well, almost, it's getting close to where it can be used to find ds. And actually, if we knew how the velocity changed with time and how the climb angle changed with time, then we could figure out this equation. But there's a problem, and that's that our thrust and drag, which are functions of velocity, and our climb angle, so our velocity and our climb angle, are controlled by the pilot. But the pilot can choose whatever they want, right? So we don't know beforehand what that's gonna be. So we can't really use this equation as it is. But as always, we're going to make some simplifying assumptions. Okay, so although we don't know v of t and we don't know gamma of t, but we're going to go ahead and assume that this whole term here, this t minus d over cos gamma, changes linearly in s. Okay, so we're going to assume that t minus d over cos gamma changes, or I'm going to say is linear in s. So what that means then is that on a plot, we're going to have, as a function of s, and this is t minus d over cos gamma, it's going to change something like this. Okay, so the integral here is the area underneath the curve, and you'll notice this is just a trapezoid, right? So we can use the trapezoidal rule, essentially. But the area of a trapezoid is just going to be the average of the two heights here times the distance. Okay, so if that's the case, then this integral here, we're going to integrate. So integrate left-hand side. And what we get then is t minus d, so t liftoff minus d liftoff, divided by cosine of gamma liftoff, but gamma liftoff is 0, so cosine of gamma liftoff is 1, so we're not going to worry about that, minus t, oh, excuse me, I'm sorry, I've got this backward. This should be, let's see. I guess it doesn't matter, right? So plus, because we're doing trapezoidal rule, plus TOC minus DOC divided by cosine gamma OC divided by 2 times SC, and that's going to equal what we had before. So WHOC plus W over 2G times VOC squared minus V liftoff squared. And we're going to call this whole term here minus, so without the SC, we're going to call this F bar sub C. So this is an average force, okay? So this equation here is what now we can use to evaluate SC with one more caveat, okay? We don't know gamma OC, so let's just talk really quickly about how we can approximate gamma OC. It's really simple, okay? So at the obstacle clearance height, we want to now be at a constant climb angle. So we want gamma OC to be constant. So we can go all the way back. Let's just scroll back to this equation right here. And we can use this equation now at the obstacle clearance location, assuming that we now have a constant velocity. So we're going to take off this last term and approximate our obstacle clearance climb angle, or our constant climb angle. So that's going to look like this. Gamma OC equals sine -1, it's the inverse sine, of TOC minus DOC divided by W. Okay, so with this equation, wow, sorry about my really terrible lines. So with this equation and this equation, we now can approximate what SC is, because SC then, if we solve this, then SC equals W over F bar sub C times HOC plus VOC squared minus V liftoff squared divided by 2G. Okay, where F sub C is this first term here, that guy, and gamma OC comes from this. And so there you have it, a way to calculate the S sub C, which then, of course, one last piece, our total FAR takeoff length is going to be SG plus SC, which is the same as SA plus SR, rotation distance. So acceleration distance plus rotation distance plus the transition distance, and that gives us our FAR takeoff distance. And of course, if you want to figure out balanced field length, you're going to be calculating a portion of your acceleration phase, your rotation phase, and your your transition phase with one engine. Okay, so there you have it.